Alright, so now the mic is on so that you won't be hearing, so that you did not hear my slurping of the noodles. Alright, we got about a week to go. Next Thursday is our last day of class, and that is when the final exam is going to be. So we only got 5 more classes, including, well, I shouldn't say 5 more classes. Let's see, including today, we got 4 classes left plus the final exam. There we go. Let's see. No, we got 5 classes and then the final exam. Yeah, we got 5 classes and the final exam. And obviously we have gotten past the point of the point where I can drop people because of lack of attendance. So it'll be interesting to see, what happens when I take roll tonight. Alright, so we got another 10 seconds or so before starting the class today. And I'm just looking at the homework assignment so that, I just have to kind of make sure that I cover enough material so that you can get started with the next lab and coding assignment. Alright, it is time, so I'm going to get started. Well, technically, I don't have to do a single thing. So technically, you know everything. You should know everything that you need to know in order to do the recursive core lab, which is about Fibonacci. Once again, it is broken up into 2 parts. The first part is due tonight. So this is your actual lab activity to do tonight. It's only worth 3 points. Okay, that's not a whole lot. The actual code that needs to be turned in, I haven't really quite decided yet, when I want to make the deadline. I'm tempted to make it Monday at 5:30, so you have the weekend to work on it. And I think that's probably, how I want to set it up, is so that you don't have to rush it, but yet have enough time to really absorb the material and be able to do the homework. So once again, technically you should know everything that you need to know in order to do this specific homework assignment by combining what you have learned in the past. So there's one program that is particularly helpful that you have seen before, and that is in params and return value. I have modified the settings of that particular lab so you can actually go back and look at it again. You cannot update your answers and get points for it. However, you can still read the questions, because in the labs, the questions actually contain a lot of information and knowledge. So I think it is helpful to be able to go back and review the labs. And specifically, the code in question 6 does relate to the current homework assignment, the one that is that you're going to be working on tonight in the lab, and also the code is due on Monday. So that's one. And then the other part that you probably want to refer to would be the program that I did, the recursive program that I did. I'm just looking through the time. I think the recursion program that I did yesterday, probably it would be helpful too. So you might jot it down and say that look into the recursion.zip file from July 20th. That is one piece that might be helpful. And then the other piece is to look into the lab that is called params and return value. Specifically, question 6, contains some really useful technique that you might find useful. So are there any questions about this? No questions? Alrighty. So if there are no questions about all of this stuff, we're going to move on. I mean, that's what happens when there are no questions. And when we are moving on, we're going to move into structures and pointers, okay? Because that's what the next lab is. I'm not going to assign it tonight, so don't worry. You're not going to get, a homework assignment on structures tonight. But it will be there tomorrow. I mean, next week, not tomorrow. Well, maybe tomorrow. I might have some overlapping between the labs. So we're going to get started to talk about structures. And before we do any work in assembly, let's go ahead and drop back to C++ first, just so that I can see if you guys are comfortable with the concept of structures. So I'm going to write now. This is not the first time you encounter structures either, because the exponent homework assignments for converting a base 10 scientific notation to base 2 quote-unquote scientific notation, that actually does involve the use of structures, even though that was not the focus. Okay, structure was not the focus of that particular homework assignment. So we'll go ahead and take a look at a fairly simple program. So we have a struct, and we define the struct as, I'll just define it as XYZ. Okay, I don't really have a specific name for this struct here. All right, so for those of you who have taken CISP360, hopefully all of you, XYZ in this case is really a class. Okay, so in other words, if you know what a class is, a struct is kind of a special kind of class. It's different from your usual class in the sense that a struct has all the members being public by default. Okay, because with a class, everything is private unless you specify otherwise. So the default is different. In C, not in C++, but in regular C, you cannot have a method defined as a part of a struct, unlike a class where you can have methods. So in many ways, structs are really just a simple version of a class. So I'm just going to pause here, just so that you guys can either type or ask questions related to what I have talked about so far before we move on, because it is meaningless to move on unless I address all the questions about the basic concept of a class or struct at this point. So I'm going to turn off the mic and let you guys ask questions. Of course, that was just an excuse for me to eat my noodles. But apparently there are no questions. Okay, so if there are no questions, I am going to move on. So we'll do a pound include, once again, stdint.h, standard integer.h. And now I can define members inside this struct. So we'll use uint_t as one member. So I define the first member as x. I now define the second member as y, except y is an array of 4 unsigned 8-bit characters. And I'll go ahead and define a signed 8-bit integer as z. This is the way I define my structure. So at this point, this is okay. So a struct like this is a cookie cutter. In other words, we don't have any cookies. We just have a cookie cutter at this point. To make use of a cookie cutter, you better prepare cookie dough. So we'll go ahead and cut out some cookies. So if I say struct xyz and then give it a name, let's call this v for variable. V is now a piece of cookie. Okay, so I'm using xyz as the cookie cutter to cut out a cookie called v when main is invoked. So once I have v, which is an object, okay, in object-oriented programming, v is an object because it is an instance of a class. In this case, we look at a struct kind of like a class. So once we have v in existence, now I can refer to members of v, and I can now say, let's initialize, member x of v to a value of 26. let's go ahead and initialize y, and we have to specify a member of y because an element because it's an array. So we'll specify what about the third element. Okay, we'll put a value of 14 into that particular element of member y of v, and v is a struct xyz, and then we'll have the member z having a value of, oh, let's make it simple, -1. And that's going to be my entire program. All right. So let me just pause again, to see if you guys have any questions about what this program means in C/C++ before we try to translate this into assembly code. Well, apparently there are no questions. So I am going to assume that this concept, of a struct was introduced properly in CISP 360. Is that correct? Because that's what the lack of question is implying. So if someone can confirm that, it'll be much appreciated, because then I can just go like, yes, we can move on. Okay, excellent. Oh, just barely. All right. Well, we are going to illustrate what this is all about. Okay. So when we look at a V, okay, so V is not really. Oh, that is going to be very regretful. Unfortunately, I am not going to ask who was your CISP 360 professor, because that would just not be good. Yeah, I'm not going to ask. I don't want to know. I don't want to know. All right. So I will see if let me see if this is going to help. Okay, in terms of the implementation. So if I explain the implementation, maybe that's going to help, because what we have here is V, but V is no longer just a simple variable. It is a variable. Okay, just like int and other things, except its type is not an int or a char or a pointer of anything. It is a struct. So that means V is cut out. Okay, if V is cut out as a piece of cookie using XYZ as a cookie cutter. So that's why V has a member X, has a member Y, also has a member Z inside of V. Those are members of V. And in order to designate a particular member, we use the dot notation. So v.x is specifying member X that is inside V as a member. v.y is referring to the array Y, which is defined up here. But with an array, we can always refer to a particular element using indexing, and that's why I'm using this particular indexing operator to specify we are looking at the third element of the array. And then Z is just a member of XYZ, except this time it is assigned integers, and that's why I can assign a -1 value to v.z. Does that help? I know this is a really kind of quick thing to do. All right. Okay. So I'm going to assume that this is okay. It is also going to be helpful. Okay, so I think this is what I can do. It's also going to be helpful to use a table to illustrate what V is actually going to look like. So V is going to have a member called X. So this is V. It has a member called X, which is, so we'll consider one cell, in column B as 1 byte. So X is going to take up one cell because it is just an unsigned 8-bit integer. Y, on the other hand, is going to take up a few cells because we have 4 elements in Y. So we have these 4 elements in Y, and then Z is over here. So when we look at V, it is all of this. Okay, all of these are parts of V. So V technically is not taking up one cell. When you refer to V, it is actually taking up 6 different cells. That's assuming things are packed, which is not necessarily the case. So I'm going to merge these cells here. OEM, there we go. So when we refer to V, we're referring to all 6 cells. When we refer to v.x, we're referring to just the first row. If we are referring to Z, we're only referring to the 6th row, and so on. So is that helping? Particularly Colton. Is this helpful? Okay, excellent. Great, great, great. All right. So the interesting about this class is, oh, you're most welcome. So the interesting about this class is we are looking into the implementation of constructs in C and C++. So sometimes, in the process of looking into the low-level implementation, it actually helps the understanding of the concept, because now we can actually get down to the bits and pieces. I should have said, bits and bytes and words and addresses. But by looking at the low-level implementation, sometimes we actually gain a clarity that is not possible in CISP360. So, let's see if that is the case, for this program. Okay, so if I were to just run this code in C, so I'm going to use gcc-g-o struct.c and then gdb struct, there we go. And I'll put a breakpoint on line 17 just after all of the initialization statements. Run the code, and now I can print. So if I were to print V, it will give me all of the members. It will tell me that member X has a value of 26, member Y is it interprets it as a string. Basically, it's still an array of chars, and then Z has a value of -1. Don't mind the \032 \377. Those are the octal representation, base 8 representation of the same value, because GDB understands these are 8-bit things, and it automatically assumes that I want to look at these as characters, which is not the case here. But I can also look into individual members, or if a individual member is an array, I can also refer to a specific element of that array. So I can do everything just like in the C syntax in GDB, which is a big clue to all of you that you should probably be using GDB to gain a good understanding of the concepts that we are going to talk about in structures. So the C code is not really super duper mysterious. So now the question is, how do we implement something like this in assembly language? So now I'm going to open up both the C code and also the assembly code right next to it. There we go. Alright, so first thing first, okay, we are going to use the usual thing, no up, jmpi to main, and then main is here, ending with a halt instruction. So that's just kind of be the template of how I write the code. But the first question is, how do we define a structure in assembly code? Well, there's no such thing. Assembly language has no concept of a structure. But it doesn't mean that we cannot represent the same thing using more primitive means. So the way I do it is I would define very specific label names like xyz_x, and I would define that to be 0. So basically what this 0 is meaning is member X is 0 byte from the beginning of a struct xyz. In other words, it is an offset. Okay, I define the label xyz_x to be a label representing the offset in number of bytes of where I can find a member that is defined inside a structure. So if that is the case, what do you think how should I define y? As an offset in number of bytes from the beginning of a structure so that I can find member y. You can assume the compiler just does the usual thing, which is the easiest, which is, the first member has the lowest address, the next one up is right next to it contiguously, and so on. So all right, so say that one more time. Can we define? But why would it be 6? I still don't understand how the 4 relates to the 6. I'm asking about the beginning. Okay, so when you look at this table here, where do I find y? Y starts here. So it is 1 byte away from the beginning of the entire structure. This is the entire structure, right? So x is right at the beginning of the entire structure. Y is 1 byte away, 1 byte off from the beginning of the entire structure. So I could just type a 1 here. But that is not the way I would like to do it, because if I choose to change x to be a 16-bit integer, then I'm going to have to redefine everything after that. So instead of doing this, I'm going to do it in a relative way, which is basically to refer to where I can find x, which is the member prior to y, and just say, hey, if I can find x, 1 byte after where x is where y is. So that's how I would do it. Then what about z? How should I define z as a label so that the label is representing where I can find member z from the beginning of the entire structure in number of bytes? You guys can give it a try. Come on. All right. Yep, 4 plus is correct. Good job. So it's xyz y4 plus. So the 1, this 1 here, is referring to the size of x in number of bytes. This 4, on the other hand, is referring to the size of y in number of bytes. Because if you think about it, where do I find z? This is where I find y, but then I have to know how big, how many bytes y is taking up, because I have to add the number of bytes that y is taking up to the offset of y in order to find the offset of z. So that's why Janelle is correct, Paul is correct as well, that it should be xyz underscore y4 plus. Okay, and we're not using plus 4 because we're using postfix notation instead of infix notation. So we're almost done here. There's one more thing to define, which is the size of a struct xyz. So that would be xyz underscore y, which is the underscore z, sorry. It is the offset to find the last member plus the size of the last member itself, which in this case is only 1 byte. So now I have these 4 labels defined. That is the way that I represent a structure in assembly language. So it is merely using labels, okay? It's not a special construct in assembly language. At the same time, it is sufficient to represent a structure in assembly language. So at this point, I'm going to so at this point, I would like to bring up the point that these offsets are assuming that the members are contiguous to each other. In other words, we don't have any filler bytes in between. In reality, they might have things in between, okay? Because there's a the compiler does not like to pack things because it wants to speed up the access of the integers. As a result, I think in this case it will still pack everything. In other words, it is going to be x, y, and z. They're all going to be contiguous, like in this picture. But if I were to use a 64-bit integer anywhere within here, then it's not going to be contiguous because if I use a 64-bit integer, the compiler would like the 64-bit integer to be aligned to an 8-byte boundary. In other words, location 0, location 8, location 16, location 24, and so on, a multiple of 8. And that has to do with the memory bus, how we can access and retrieve the entire 64-bit integer in one single memory access if it is aligned, if the address is a multiple of 8. If it is not, because of the way memory is organized, then we'll have to use 2 memory accesses in order to access the same 64-bit integer. So for efficiency, purposes, the compiler would, definitely not pack things when we start to have multi-byte integers. In this case, they're all single-byte integers, and that's why it's not going to be an issue. I believe, the C code is going to have everything packed as well. All right. Well, I'm curious. Okay, I want to find out whether everything is in fact, packed in the C code. How do I find out? So this is a question directed to you guys. I want you to think about what tools do we have and how do we make use of those tools in order to find out whether those members inside the structure are in fact packed or not. So I'm gonna let you guys think about it when I eat my noodles. I think this is a great way. I should have used this from the beginning of the semester to make sure that I give you guys enough time to think about something and ask questions. More instant noodles in the future, definitely. All right, Paul is typing something. I'm gonna wait for that. Yes, all right. Okay, so we got a winner. So when we get to the program, so this time I don't even have to wait until I get to the return statement. I can put a breakpoint on line 14 as long as the program is loaded and in execution. I can do this trick. So I just run the program. This is before the first assignment statement. So now I can say, tell me where is V itself, okay? Where is the starting point of the entire structure? It is located at this location. We only have to pay attention to the last 2 digits in hexadecimal. So in this case, it is EA. So now we ask, where do I find X? And not surprisingly, it is the same, right? Because X is right at the beginning of the entire structure. So this is why the offset of X from the beginning of the structure is 0. So here's the moment of truth, is where do I find Y? Because if packing is used, then Y should be EB, which is the next available location. But if it is aligned, then it's going to be somewhere else. So now we can see that it's just EB. It is packed, okay? And now the question is, where do I find Z? Well, it's going to be, I'm going to guess, it is 4 bytes from EB. So if you count 4 bytes from EB, it should be EF. And indeed, it is EF. So now the question is, what about the size of a structure? Because just because we got the offset of the members right, doesn't necessarily mean we got the size right either. Because maybe, just maybe, the compiler says, I want every single structure to be aligned by 8 bytes, okay? And we can print size of, okay? So with size of, there are 2 ways to use it in this case. You can always ask what is the size of a type. That will work. You can also ask it what is the size of an object. That will work as well. So in this case, it is 6. So this part is very important, because if you want to write a program where part of the program is written in assembly and part of the program is written in C, C++, and you want to you want the subroutines to call each other, so you want C to call assembly and then assembly to call back to C, they need to have the same understanding of how a structure is, guess what, structured. Okay, and in this case we have an identical understanding of how XYZ is structured. So in theory, the C code can now call the assembly code can call the C code. Now obviously the architectures are entirely different in this case, and it's not going to work. However, there are many cases where you would be in a situation where you have an architecture. You can write certain portions of a program in C, and you have to write certain portions of a program in assembly. And in those cases, being able to understand how a structure is constructed by the compiler becomes very, very important. So I'm going to use this opportunity to also ask you guys a question. What kind of program is almost mandatory to have at least a part of the program written in assembly, while maybe the majority of the code is written in C? Mm, Not necessarily a compiler, but an operating system. So when you're dealing with an operating system, there are portions of the code, especially in the kernel of an operating system, that has to be written in assembly, because the um, the the work to be done by the code is not something that is expressible in C or C++. And C and C++ are already really low level compared to other high level programming languages. I'll give you an example. Okay, in Java, Java has no concept of a pointer. So Java is really a high level concept, a high level programming language, because it lacks the low level constructs in order to do some of the quote unquote dirty work when you're writing an operating system. So when you look into the source code of, say, Linux or Mac OS X or Windows, but Windows source code is definitely proprietary, so I doubt anyone here has access to that source code. But you will find most of the code to be written in C, maybe a little bit of C++. I really doubt that is the case. But you will also find at least some portion of the code, probably between 5 to 10% of the code, that is written in assembly, because it must be written in assembly, certain portions of that code. All right. So now, what do we do? Well, we go back and we translate the rest of the program. So now we go here, and the first thing we need to do is to say, what is the stack going to look like when the code of main is about to execute? Okay, in other words, how do I want the stack to look like in main? Well, v is just like any other local variable. It lives on the stack. Okay, to be more exact, it is a part of the frame of the subroutine that contains it. Okay, then what are we going to do about that? So what I'm going to do is I'm going to give you a map of the frame for main in this case. Now remember, main is not being called from anywhere else, so there's no return address on the stack. But we do have the local variable v on the stack. So once again, I'm using the convention of a line that is on top of another line is representing a construct that has a higher address. So of all of the members of v, z is the one that has the highest address, and then followed by the last element of y, and then followed by the second last element of y, and then followed by the second element of y, and then followed by the first element of y. Yes, it is very boring. And then followed by the first member of y. This is what the stack is supposed to look like. Okay, this is the local variable living on the stack. Okay, now how do we do this? And by the way, because there are no other local variables, so once we are done allocating for local variable v, we are done, which means the stack pointer should be pointing to the beginning of the entire structure of v itself, which is also the address of v.x. Okay, so how do we do this? How do we allocate this much space on the stack so that we will have room for my local variable v to exist on the stack. There are several ways to do it. Some people will say, well, we can just decrement d 6 times. That'll work. Not the best way to do it, but it'll work. So the next thing we say, maybe we just need to subtract 6 from the stack pointer. The answer is yes, we could do that. So I'm going to ask you first, how do we do that? Oh, there's a subtraction instruction. We specify the register, and then we say how much we're subtracting from register D. There we go. Nope, not going to work. How do I know this is not going to work? Because the syntax highlighter doesn't like it. So what is going on here? Sub only takes both, it needs both operands to be registers. In other words, we can only subtract the content of the value of a register from the value of another register. Possibly another register. It can be the same register. Very seldom, okay, but we do that. So this is not going to work. And someone's going to say, oh, that's easy. We just have to do LDI, put 6 into a particular register, say A, and then we subtract A from D. Yep, that will work. But I would still say this approach sucks. Okay, it sucks because if I choose to redefine, XYZ and add or subtract, members, this is all going to be changed, and this is all going to, it should be changed too. Okay. So maybe we should do this, right? Maybe we should just refer to the size of XYZ, because if we change all of these definitions here, because we change all of these definitions here, then we should still have the right size over here to subtract from D. That would be correct. Okay, so at this point, I'm going to say that is okay. But remember, we also want to define labels to find our local variables. So we have main underscore v being defined to be 0, because the first byte of v is where the stack pointer points to once we have allocated the space for it. Okay, so now labels are quote unquote free. Okay, they are free because they don't take up any opcode in the RAM when the program runs. These are all constructs when we are assembling the program. So that means if you want to define more labels just so that you can keep track of things in a more symbolic way, hey, it's all okay. So if I want to calculate, okay, what is the total number of bytes that I need for all the local variables in main, I'll go ahead and define something like this, local var size, and I'm going to do a LVS here, which stands for local variable size. How should I do this? Now I can say 6 because we only got v, and v takes up 6 bytes. So when we want to find out how many bytes we need to reserve for local variables in main, it's just 6. But now, this literal integer 6 is no longer dependent on all of these nice labels that we have defined earlier. That's not going to work. Okay, maybe we can just make it XYZ size. Right? I mean, that's the same thing. That's still not a very good approach, because what if I want to add more local variables into main? Then it's not just going to be the size of struct XYZ, because I might have some other stuff in it. Okay, if that's not going to work, what is it going to be? It's going to be the last local variable that I have allocated the space for, and the size of that local variable. So I'm going to add XYZ underscore size to this. Now I have the best way to define the number of bytes that I need to allocate for local variables. Now, does that mean if you guys do it in any other way that I'm going to take points off? No, not really. But it does mean that this is the approach that will best isolate changes to not only how struct XYZ is defined, but also how I define local variables in main from the allocation. Okay, so my idea is I don't want to make my code brittle, because if I were to just put a 6 over here, that makes the code really brittle. Okay, so once I have this label, I want to use the label. So now I say, let's go ahead and subtract this much from the stack pointer in order to allocate for all of my local variable. And my practice, right? If I start something, I'm going to end it right away, just so that I don't forget. So the code to allocate is here, the code to deallocate is here. So in between, I can now feel comfortable and just go like, okay, now I don't have to worry about deallocating the local variables later on, because it's already done. Okay. Do we have any questions at this point about this code? I'm gonna turn off the mic. All right, I'm not seeing any questions. Well, if I'm not seeing any questions, we're gonna move on to how do we do something like this? So I'll do it the long way first. Okay, I'll do it the long way first. The right hand side is easy. The right hand side is just 26. In fact, I can probably do this last, okay, because it's not really the point. But I'm gonna do it here anyway. So this is the right hand side of the assignment. Now we need to deal with the left hand side, which looks kind of troublesome because we got V, we got X, and they're basically specifying something on the stack. So we know register D is probably involved in all of this. How do we do this? Well, we do it step by step. So the way we do it step by step is, let's go find V first. Okay. Now V is a local variable. So the way we find the address of a local variable, I have talked about it many times already. Okay, especially with labels like this, defined already with main underscore V, defined as the offset from where the stack pointer points to. So to find the address of V is just like this. Okay, it's loading main underscore V, the label, into register B, and then we say add BD. Because register B originally had the offset to the local variable, now that we add the offset to the stack pointer, we have the actual address. But then you will go like, but that's just the beginning of the entire structure. We want to access a specific member. But that's okay, because I can now use another label. Okay, so let's say label another register. Sorry, I misspoke. We can use another register to store the offset from the beginning of the structure to the member that I want to access. That's XYZ underscore X. That's the whole purpose of this label, is to use a symbolic name so that I can refer to the symbolic name as the number of bytes as an offset from the beginning of a struct XYZ to member X. Okay, so then I just have to add that also to register B, and now register B has the address of member X of V as a local variable that is living in the stack. All right, I'm just going to pause here because I know this is a little bit to digest. Okay, so I'm going to pause and eat some more noodle, drink some more coffee. But I want you guys to look at this and see if you have any questions. All right, looks like there are no questions about this one. All right, so now we are just lacking one last instruction, which is the store. Register B has the address of member X of local variable V. Register A has the value of the right hand side, so STBA is going to get the job done. Moving on to the second line. So the second line looks a little bit more complicated because y is not just an integer, it is an array of integers, and we want to get to element 2 specifically. How are we going to do this? Well, same thing, one step at a time, okay? So once again, we load A with the right hand side, which is just 14. And then we load B with the offset of the local variable itself. And then we add BD, we add D to B, so that we get to the address of the entire structure, okay, of the local variable V. Then we look at this and go like, we need to get to member Y, okay? So I know we eventually want to get to element 2 of the array in the array, but we need to get to the array first before we can get to the third element of the array. Okay, so that means we just need to use the offset that we defined earlier, which is xyz underscore y, add that much to the address of the entire structure. So at this point, B is the address of the entire array, or I should say, B is the address of the first byte of array Y as a member of struct xyz, which V is an instance of. And now we want to get to the second, or the third, excuse me, the third element. BC, sorry. Thank you. I'm glad someone is paying attention. So add BC, because BC has the offset to member Y from the beginning of the structure. So now we go like, how many bytes do I need to add to B in order to end up at element 2? Well, since each element only takes up 1 byte, so it is just adding 2. So we want to add 2 to B again, like that. So at this point, register B would have the address of element 2 of member Y of V, which is of type struct xyz. Now, once again, I'm not putting any comments here. I'm just verbally spelling out the meaning of each register, which means when I'm done with this, remind me to upload the code into Discord so that you guys can fill in the blanks. Now, if you're already filling in all of those comments right now on the side, that's okay too. Okay, but I'm gonna give you the source code so that you can actually do it later on if you want to. Alright, so now it's just a STBA and we're done. Okay, so we are now on to the third line here, which is kind of identical to the first one, except we're using member Z. I'm getting lazy, so I'm gonna get up here. This is line 21, this is line 27, yank. This is how we do copy in VI, and then paste P, and then we just have to change a few things. Instead of member X, now we are referring to member Z. Instead of 26, we are now specifying -1, and the rest are the same. Okay, so now we are ready to test run this code and see whether it's right or not. But before we can do that, I really need to know what is correct. What is the stack supposed to look like when this is all done, right? But that is why this table is coming in handy. Because what I can do now is I can insert one additional column to here. Oh, right, there we go. It just needs to be a little bit wider, because I need to now indicate the actual location in RAM. This is the last location. Oh, I got everything flipped, reversed. Darn it. Okay, I'm just trying to figure out, is there a quick way to do this? Because I don't want to change the way I use a higher cell to mean a higher location. So I'm just trying to figure out, is there a way to I know exactly what to do. I can sort this in reverse order. There we go. Good thing I use XYZ in that order as the names of the members. Alright, so we want to do sort, and we want to sort. Let's see, descending is correct. There we go. Current selection. There we go. Nice, isn't it? FE, FD, FC. I think it actually knows how to do this. If I were to extend the extension, maybe. There we go. All right. So now that we know the actual exact memory location corresponding to each and every single byte inside V, which is of the type struct XYZ, and we also know what value is supposed to go into 3 specific spots, right? So we know X is supposed to get 26, but 26 is in decimal. When we go to the trace analyzer, everything is in hexadecimal. Okay, that's just 1A. It's 1A because the 1 means we have 1/16, and then the A is a 10, so 16 plus 10 is 26. So there we go. And then the 14 is going to Y bracket 2, which is here. 14 is 0, let me see, E, because 15 is F. And now we have Z being -1 all the way over here. And the bit pattern of -1, when we have 8 bits, will be all 8 ones, right? So it will be 1 1 1 1 1 1 1 1 in hexadecimal. That's FF. The rest of the locations are not initialized. Okay, now we know that when Logisim runs, it would automatically initialize every single location to zeros. So all of these locations would be zeros. But technically speaking, when you look at the C code, they are simply uninitialized. So they would just be whatever content those locations had before main was called. Okay, so you do not want to count on these locations being initialized to zeros. Okay. All right. So now that we know what the program is supposed to do, what location in RAM is supposed to get what content, it's time to run it. So let's go ahead and give it a try. So I'm gonna go back to my handy dandy script, which is in CISP310. Reverse spider, and we'll say submit, and the source code is /tam/struct.ttpasm. All right, so it's all done. Now we go back to the assembler and see whether it works or not. You guys can go to the assembler just to check out the execution and stuff like that. This is why Google Drive is so great for teaching, because you guys can go check out the documents anytime you want to. All right, so we want to look at, I think it's summary. Yep. There are only 51 lines in the trace. Okay, that's a pretty short one. And when we look at analysis, which is the trace analysis, we want to find those specific operations. I can now specify A1 so that we go all the way to the top. Oh, okay. It just goes okay, I see. I see. All right. So this is from the allocation. We are decreasing the stack pointer by 6 to allocate 6 bytes because we have one single local variable on the stack, and that single local variable uses up 6 bytes. The first thing we store is a 1A into FA. Let's check. A 1A into FA, that's our V. The second store is a 0E into location FD. 0E into location FD, that's our element 2 of Y in V. And then the very last store is a FF into location FF, and that's how we store the -1 into member Z of V. So now we are all done here. So that's it. I mean, this is my demonstration of how we utilize the concept of structures in assembly code. So I'll let you guys digest this a little bit and see if there are any questions. If there are no questions, then we're going to move on to a peculiar program next. Okay, so we'll get to that program when you guys confirm there are no questions. The answer to Paul's question is yes. So when you have 16-bit integers, then each one will take up 2 bytes. When you have 32-bit integers, each one is going to take up 4 bytes. You can, yeah, so you kind of have to do it by hand in the code. So when you define the size of each, or when you define the offset, you kind of have to remember what is the number of bytes per member in the structure. There's no quick and easy way to do that conversion, unfortunately. Well, I lied. I lied. There's a way to do it. Okay, let me show you how this is going to be done. So let me go back to the original program first. Pop D. So this is only going to be illustrable in the C code. So what you can do in real world, okay, this is like in real world when you have a real architecture where you're writing part of the code in assembly and part of the code in C++. So what you can do is to do something like this. Darn it. I better not overwrite the original program because I want to preserve struct.c the way it is, and we'll go and I'll change the name to labels.c in this particular one. All right. Okay, good. All right. So what we'll do in this case, now this one is just to answer Paul's question. However, some of you may have an opportunity to do this kind of coding in your future, so it might actually come in handy for some of you. So the way I would do this is I'm going to use printf, and then I'll create the label definition right here. So I'm going to do xyz underscore x, and then colon, and then %d, and then a line feed character. And then what I would do is I'm going to cast all the addresses. In this case, I have the address of v.x and into a char pointer. And let me use extra parentheses to make it clear. And then we have another cast, and this time it's just the address of v. So I'm going to have lines like this, okay? One for y, and then one for z. It is still not super duper, automatic, because if I do change or add more members, this cannot be automatically taking care of that. And I have not found a way to automatically take care of the addition or the editing of members. But at least this is a way to do it, okay? And then the last one is going to be just the size of. Like that. And we're just going to print size of v. And obviously I'm forgetting all the semicolons at the end because I've been doing too much JavaScript coding. There we go. So, oh, typo in size of. Oh, right. There we go. Oh, there we go. And then we do a gcc -o labels.c, and then run labels. So when it runs, it gives us all the correct offsets. So what I would do in a commercial setting is I'm going to use a makefile so that I use the output of labels and put it into a .h file or a .ttpasm file, and then I will basically have another tool to merge this header with the rest of the code. In other words, I'm going to use a programmatic way to generate the labels so that I make sure that the assembly code and the C code will have the same understanding of the size and also the offset to members. Yeah, you have to see the makefile that I created, for this kind of purpose, because the makefile has to first make the program called labels, and that depends on the definition of the structure, and then from that it will generate a file that is dependent on in order to do the assembling and so on. So all of this may prompt certain people to ask the question is like, Tech, are we really sure this stuff is useful? This sounds like a lot of trouble for, because you like to teach this class. And, I really doubt that in real world it will have any use of this kind of stuff. Well, I cannot say this is real world, but I can tell you this is an application. So I'm just going to go to my page here. Unfortunately, it doesn't work that way because I lost my index page. Let's see. I think it's develops. There we go. All right. So I made a real-time kernel, and the documentation of the real-time kernel is right here. I'm not going to spend time in this class to talk about what is a real-time kernel, but I'll give you the API, the application program interface, application programming interface. And you can see, how to, in order to initialize the real-time kernel, you call this particular subroutine. Looks like a C program, right? It returns a void. The name is RTK initialize. It takes a pointer to a struct thread, and it takes a pointer to a struct queue. But guess what? The subroutine itself is written 100% in assembly language. So I'm designing this particular real-time kernel so that you can just use a regular C compiler to write your code. But once you compile your code and link it with this particular real-time kernel, then you will be able to use multi-threading and all kinds of good stuff for embedded real-time control. So so this is one of the application. Now, if someone is to accuse and go like, but Tech, this is your stuff again. So you're using your stuff to justify the way you teach this class. That is still circular reasoning. I cannot dispute that particular argument because I am using examples of my own stuff. But this is actually useful in the real world. Okay, real-time kernels are real. Yeah, I know that sounds really strange, but they are real in real world. Any type of robotic application is going to need a real-time kernel. If you play with Arduinos, for instance, Arduinos do not come with a real-time kernel, which is a shame because it really makes certain things difficult to express. I'm not going to get too deeply into real-time kernels and whatnot, but I can just assure you that if you do any type of embedded system development, you will encounter real-time kernels and you'll be pretty close to the hardware level, and in many cases you'll be writing code in assembly language as well. And here's a search for that particular term: embedded system development. So if you look up embedded system development as a definition in Wikipedia, or embedded system in general, it's interesting. I believe there's a lot of opportunities in embedded systems because these things go into everything. Okay, okay, I'll give you an example. Last time I read a car article, that was probably about 5 years, 10 years ago. They said, if you just buy the cheapest, the dirt cheap Econobox from a dealership now, okay, back then, 5, 10 years ago, Each car comes with 14 computers. Okay, there's a special computer just for anti-lock brake control. There's a processor for engine control, emission control, and so on and so on. Okay, all of those belong to the category of embedded system. You're not going to find a Windows box controlling the anti-lock brakes. I hope you guys understand why that would not be a good idea. What if Windows decide I think I need to update now, and you're hitting a corner and go like, oh no, I need to hit the brakes really hard. Guess what? Windows says, I'll be back. Just hold on a second here. I'll be back. Yeah, that won't be a very pretty situation. No, no. So embedded systems is a very specialized type of programming, but that makes it one, interesting, kind of fun. Two, if you're good at this, you will be in a niche, market where there's not really a whole lot of competition. Because a lot of people don't want to get into embedded system programming just because it is really kind of specialized. And it is also related to robotics, motion control. Those are all a part of embedded system control. So anyway, I digressed. Yes, I did. Anyway, so getting back to the program, I don't see any questions other than generalizing and use different size elements. So now let's go ahead and write another program. Okay, so we'll go ahead and write the program in C first, and then we'll make it change it into assembly code. And I'm going to call this list. Okay, list stands for linked list. And some people may say, but this is a concept in CISP360. No, not 360. This is 430. Put it here because I think I'm not asking you guys to write this code. I'm just asking you to understand this code, and that I think is okay. Not a problem. Should not be a problem. So once again, I'll define a struct. This time I call it a node. Okay. Inside the node, I'm going to use uint 8_t, a value. Okay, so v is just a value. And then the next one is going to be interesting because I'm going to make the next one struct node and then asterisk. I'll just call it n. Okay, there we go. So just looking at struct node, the way it's defined, someone may say, oh, that's recursive. Well, actually, it is not recursive. Someone's going to say that should not be possible because we are in the middle of defining a struct node, and one of the member is a struct node. No, that's not what the code says. Okay, because what n is not a struct node. N is a pointer to a struct node. All right. Does everybody see? Can everybody differentiate a struct node from a pointer to a struct node? I'll give you an analogy. It will immediately make this easy to understand. Look at a node as a house, and look at the address, a pointer to a house as the address of a house. Okay? You cannot contain a house in a house, but you can certainly contain the address of another house in a house. Because all it takes is a little slip of paper that has a street number, street name, city, state, zip code. That's it. Alright, so it is okay to have a pointer to a structure that is being defined. Alright, so if this is okay, how are we going to use this, right? So this is how I would define it. I'm using initialized global variables in this case, just because I want to illustrate the point of what we can do with this. So I'm going to define a global variable c, which is of struct node type, and I will make it an initialized global variable. So now I have to supply the values of v as well as n. So for v, I'm just going to randomly pick a value. Let's say 25. And for node C, I'm going to use a null pointer to specify struct node the address member n, which is an address of a struct node. So it's just going to be a null here. Now, null is really just a fancy way of saying 0. In other words, if I were to specify a 0 here, the compiler would just go like, okay, I understand what you mean. Because that's what null, N-U-L-L, translates to. It really is just 0. And I'll define another node here, which is, I'll call B in this case. And it has V as a value of, say, 14. And now this time it's going to be interesting because I'm going to use ampersand C to define the value of member n of B as a global variable. And now I use struct node A, and let's make the V value to be, oh, I don't know, 65. And then I will use ampersand B to be the value of member n. So this is how I define these three struct node. And we'll do a main and return 0. Okay, we are not even going to bother with any actual code because I just want to get into the debugger and show you what I can do with the three global variables, A, B, and C. So now we do a gcc-g-o. There we go. And we'll put a breakpoint on main like that. Run. Okay, so now we can say, okay, tell me what is in A. That's A. And you can see how GDB is pretty smart because it understands what n is. It understands that n is an address of a struct node and it is the address of B as a global variable. So we can now say, part of A as a global variable is a way for me to find B. In other words, B is not a part of A. A only knows a way to find B. Okay, B is not a component of A. So now I can say, tell me what is B.n. Okay, tell me what is the dereferenced of B.n, and it's just B because that is B also. So if I say, what do you think B.n is? It's a pointer to C. If I dereference it, it is just C itself, but I can also say print C. Identical. Same thing. So are we doing okay so far with this concept? I'm going to pause here, let you guys think about it a little bit, look at the print statements, and see if you have any questions. Oh, sorry, I forgot to turn off my mic, so you guys had to listen to all that slurping. Looks like there are no questions. Alright, well, if there are no questions, I'm going to continue with this program because I intend to do something interesting about those global variables. So in main, I'm going to use a struct node, and this time it is a pointer to a struct node. I'll call this P, okay, for pointer. And I'm going to initialize P to be the address of A, which is a global variable of the type struct node. And I'm going to say, as long as P is not 0, do the following. What do I want to do? Well, let's see. I'm going to do this. P is P points to N, like that. So I'm going to pause here because I think some of you may not be familiar with this notation. Is that correct? If we are all familiar with this notation, I don't need to explain it, but if not, I can explain it. Okay. All right, so I will go ahead and explain it. All right, so this notation means exactly that these two statements are the same. They mean exactly the same thing, just different notations. All right, so I will let you look at these two lines, okay? These two lines, okay, let me refer to line numbers. So line 19 and line 20 mean exactly the same thing. Does that help explain what this notation is? The little thing that looks like a right arrow. Because we are combining concepts now. Oh, okay, excellent. Okay, so we got one confirmation. We are combining symbols and operators here. P itself is a pointer to a struct node. So when we dereference P, we get to a struct node. Now, with a struct node, we can refer to a specific member using the dot notation. So the right arrow notation really is just a shorthand. All it is a shorthand to basically say, I want to refer to member N of the structure that is pointed to by P in this case, which is identical of saying, let's dereference P first, get to the structure, and then we want to access member N of that structure. So these two lines are actually identical, even though in industry you don't, well, okay, seldom find people using line 20. Most people in industry would use line 19 as the notation to refer to a member of a structure that is pointed to by a pointer. And by the way, this kind of stuff, you would not find it in Java because Java has no pointers. Java only has the concept of a reference, so everything would use a dot notation because there's no such thing as dereferencing. I'm just looking at the time and see how much time we got. Okay, so we got just enough time to finish maybe the fun part of this program. I'm gonna make this program so that it actually does some work by itself, so I don't have to use the debugger to illustrate everything. So I'm just gonna do a printf here, which is the same thing as a cout, except it's a little bit more archaic. Okay. So I want to print a unsigned integer. I want to find out how to print. Yeah, I think that should be fine. So there we go, and I need to typecast P points to V. The casting is needed because this notation expects a 64-bit unsigned integer, and V is only 8-bit wide. So I need to cast it to a 64-bit integer in order to print correctly, so that we don't end up with, let's see, 7 bytes of garbage being printed. There we go. Okay, so let me ask you guys, what do you think this program is going to print? If I just tell you this line is going to print member V of the struct node that is pointed to by P, what do you think is going to be printed when this program runs? Alright, so let's go ahead and start with the analysis of this program. P is initialized to be the address of A. So in the first iteration, okay, first of all, P is not null anymore because the address of A is not 0. No, it doesn't print the address of A. It prints member V of A, which is 65. So that's what the printf statement is going to do in the first iteration, is it prints 65. Line 21 is going to say, I want to use member N of the structure that is pointed to by P to update P itself. So it's going to use the address of B to update P. So in the next iteration, P would be the address of B. So by the time we get to the printf statement, it's going to print member V of B as our global variable, which is 14. And then it's going to update P again using member N of the structure that P is pointing to, which in this case is just struct node B. That turns out to be the address of C. So P is going to end up with the address of C at the end of the second iteration of this while loop. So at the beginning of the third iteration, P is not null because it is the address of C. It gets into the body. It's going to print member V of global variable C, which is 25. And it's going to update P again. But this time it's going to use 0, which is null, to update P. So at the beginning of what would have become the fourth iteration, but it's going to terminate because P is now a 0. P is now null, and as a result, the loop is going to exit. So what this loop is going to do is it's going to print 65, 14, 25, and then it should exit. All right, so let's find out whether that's what this program is going to do or not. So with this one, okay, let's GCC it first, compile, and I'm just going to run it by itself, just so that we can see the output. So it does print just 65, 14, and 25. I'm looking at the time. I won't have enough time today to finish the assembly code, but I will give this code to you through the Discord channel because I want you to not to stare at the code, but to try to understand what is happening in the C code. And then on next Monday, we'll talk about the implementation of this code in assembly code. Okay. So we are done with the lecture portion. Let me point you to the lab tonight. So the lab tonight is recursive call. And once again, we have already touched on all of these topics. All the necessary topics are already discussed in the past. And I'm going to open it up. And the passcode is fib for Fibonacci. There we go. I'll put it into the text channel. That's your access code. And I'll make it due tonight, which is July 21st, 8:20 p.m. There are only 3 points, by the way, with the quote-unquote lab portion, so that really should not take long. However, that's not all you need to do because there's also the coding part of this lab. So the coding part of this lab, I'll make it due next Monday at 5:30, which is the quote-unquote assignment. It's indented because it is a component of the lab, but this part is not due tonight. This part is due next Monday at 5:30 p.m. So the description is here. Let me specify the due date. This one does not have a passcode, so there's no access code to this part. You do have to turn in a TTP ASM file, which is the mnemonic file. I don't want the opcode. If people turn in the opcode, they will not get points. I need the mnemonic. So this is going to be on the 26th at 5:30 p.m. It might take you a little bit of time to look at the resources, to go back to the resources that I mentioned at the beginning of this class, to understand how they relate to the homework assignment. So I would definitely not sit on the homework until like Monday to work on it, because it might take you some time to review what we have talked about in the past, and also make connections to this specific homework assignment. So I would strongly suggest that when you're done with the 3-point lab tonight, move on and get started with this specific coding example. What I'll do tomorrow is to continue with the linked list program. I'll give you the assembly code to implement the C code, but also at the same time, I am also going to give you some suggestion of how to test your program with this particular lab. But you might want to get started at least thinking and planning, and also referring back to the material that I mentioned at the beginning of this class, and see if you have any questions, and use the lab time to ask those questions. That will be a good use of your time and mine. Other than that, I think we are done. I'm gonna sign off, and I'll be back in a few minutes. If you have any questions, use the text channel, and I'll be there. All right. Have a nice evening.